So thank you for having me. This is wonderful. This has been great. So I want to start by giving a little bit of feel for the Chicago Math Teacher Circle, which I've been working with for like 8 years now or something. We're kind of into like really free-form problem solving. So we like to just give our participants a problem to think about. They hang out and work on it and eat some food for like an hour and a half, and we chat. This is roughly what we like to do. We do some warm-ups. We try to get people in the right kind of problem-solving set of mind first. Well, one of my favorite warm-ups is this one that's on the back of a shirt that I got from AIM once. So we use this one sometimes, but we have a whole bunch of others we use. And we have a poster, which I meant to cut and paste an image of it, but it's actually kind of appropriate to not have it because we change what it says all the time. But it always has at the top this phrase like do something. You need to experiment, you need to play with it, and you need to go on. So that's kind of our philosophy. This session was called Favorite Math Circle Problem, which I love the session title. I think it's great. It's also difficult because I have at least like 10 favorite math problems. So it's tricky, but this is the one I chose as my favorite today. I don't guarantee I would stand by that tomorrow. But so the problem is a ninja tosses a watermelon in the air. They have a sword. They slice the thing up 10 times. How many pieces can they make? Yeah, and we just sort of state that and let people start talking. And well, I mean, the first thing is you need clarifications, right? Like that question by itself is not quite precise. So people will start asking questions and getting clarifications. And well, we always have to clarify their straight cuts. If you're allowed to cut it in a curvy way, you can get like as many pieces as you want with 2 cuts. So they kind of have to be straight or it doesn't make sense. This one always requires some talking. So like what I mean by this is here's a picture of a watermelon. You toss it, you cut it. So this little circle in the middle is supposed to be a cut. It's been cut, but it's in the air and it's a sharp sword and they just stay there. Yeah. So when you cut it again, maybe I'll cut it with a different color, like I cut it here or something. Well, it's still, now it's in like how many? 1, 2, 3, 4 pieces and it's still in the air and nothing has moved. Yeah. So we always have to clarify the question. And then the question itself is actually completely unclear. How many pieces can you make? Well, there's lots of different numbers you can make. So I've actually sometimes let people just explore that for a while. But in some sense, the most interesting question is what's the maximum? Like you're trying to cut it up into lots of pieces. So usually I guide them towards there, but I actually did once run this and just let people like go nuts with, well, how many different sets of numbers can I get? And that was kind of fun too. So that's the problem. And what I would love to do is make this interactive and let you work on it for 10 minutes. But there's a proof that I don't have 10 minutes to do that since it's a 10-minute talk. So I'm going to spoil some things and show some things about the solution, but I'm sorry about that. So why do I love this question? Obviously, you should do a smaller case, right? It's 10 cuts. 10 is too many. You should try to do it with 1 cut, then 2 cut, then 3 cut, then 4 cut, then 5 cut. But when you do that, you start drawing it on the page and you start cutting, and people just naturally do the 2-dimensional case instead, and often don't even notice they've simplified it. And you have to be like, no, you just simplified to 2 dimensions, which is great, but you need to do it. But then once you've simplified to 2 dimensions, you should simplify to 1 dimension. Oh, well, now it's easy, right? Every time you cut it, you just get 1 more piece. Well, and then of course you should organize your data. So you should say, oh, now I'm calculating cuts and number of dimensions, and with 0 cuts, I have 1 piece, and then 2, then 3, then 4, then 5. Okay, this is great. And then you do 2 dimensions. Probably you can't see that color. Let me get a better color. There we go. Cut it. All right, so you get 2. You cut it again, you get 4. Cut it again. Well, this one sometimes causes trouble, but you get 7. You cut it again. Oh my gosh, this is always really tricky, but I got 4 more pieces. I get 11, and you start getting some data. Well, and then you can do 3 dimensions and start getting some data if you want to, if you haven't seen any patterns yet. And then you get 1, 2, 4, 8, 15, and then it goes on. And at some point, there's like 2 ways to solve this. You can notice these patterns. This 11 is somehow 7 plus 4. This, if you get lots of data, 37 is 8 plus 29. 64 is 22 plus 42. So there's patterns in this table. You can just recognize it. You also should notice, well, there's like lots of powers of 2 here, and even some like special extra powers of 2 hidden over here. That's kind of interesting. But you know, there's a recursion here you can just sort of see. But oh, I need a different color. The recursion is actually visible in the geometry. So here's, let's see if I can highlight. Let's say I just did that cut in 2 dimensions. How many new pieces have I created? Well, I created one here, one here, one here, one here. It's one for each segment of that line. So like, not only do you see pattern recognition, like you really get the next case from the previous case. And oh, wow, you've solved the problem. So that's most of what we do. But in fact, it's not all of what we do. So extensions, any good thing has extensions. You inevitably get people asking, what's the formula? You know, I've done this actually with different groups. I've done this with groups ranging from like 4th graders through like college seniors and teachers. So it's different in different groups, but someone usually wants to do formulas, and there's polynomial formulas. Okay. And you can sort of talk about that. And it leads possibly to a nice discussion of like taking differences. So you take one sequence and you take the differences and you get a different sequence. And why are these polynomials? Well, it's because the differences are eventually constant. Or if you like, you can bring in this triangle we've probably all heard of. And in fact, these answers are, you take for the 3 dimensions, you take the sum of the first 4 entries from the left on Pascal's triangle, and that will be the answer. And I actually don't know a super deep reason why that's true. So that's something I've asked people all the time. Is there a really good reason? Is there a bijection or something? Like, tell me a really good reason. I don't know one. I can prove it inductively, but I don't like to. If I justify it, I like to say, well, both these sums and those things are obviously polynomials, and they both start with powers of 2 for as many terms as possible, have to be the same polynomial. So I actually don't know any deeper reason than that in my mind, but it does match with these Pascal's triangle sums. So bring that in. So anyway, this is just a problem I love, and that's what I wanted to say about it. Do I have anything else here? Oh yeah, I'll do a plug for this. I always end with this, which I learned from AIM in 2014, I think. We always end with some reflection, and we always get some like amazing insights from teachers into all kinds of things. So I wanted to plug that. We just do very free form answering of these.